Hello everybody. Today we'll compare octave bands of different frequency resolution. So when sound recordings are performed, they're performed in the time domain. In order to make sense of the data, you need to view it in the frequency domain, for which you need to perform an FFT analysis. Now, octave analysis is one such analysis which helps you view the data in the frequency domain in especially octave bands. So there are octave bands of different frequency resolution, and the most basic is 1 by 1 octave bands, and there is higher resolution such as 1/3, 1/9, 1/12, 1/24, and so on. So let's say we take the time signal, perform the octave 1 by 1 analysis, and view the frequency spectrum. So this is how it's going to look like. The y-axis is the sound pressure level in dBA scale, and the x-axis is 1 by 1 octave band frequency, so it's lower resolution. And here we see that the 2000 hertz band is the most dominant. Now, we move on and we take the same time signal and perform the analysis with the higher resolution octave band, such as the 1/3 octave band. So each 1 by 1 octave band is viewed in 3x resolutions, so we get 3 times more resolution, and we see the frequency spectrum here. The y-axis is still the same, but the x-axis is 1/3 octave band frequencies instead of 1 by 1. And we see here that the 2500 hertz is the most dominant. We repeat the same process for 1 by 9 octave band, so it's even higher resolution, and we have this frequency spectrum. Now, we will compare two different resolutions together in the same graph. So let's say, for example, we're comparing octave 1 by 1 and octave 1 by 9 on the same graph. On the y-axis is still the sound pressure level. On the x-axis, you have multiple frequencies, and it's shared between octave 1 by 1 and octave 1 by 9 bands. So at the first glance, it may look like octave 1 by 1 is different compared to octave 1 by 9. We see that there is a huge difference between the two the levels in each band. Why is that? And we may have a question that which one is accurate? Well, technically both are accurate. So first, you may look at the single value down below. They both are same. I will get to how we calculated that. But first, consider this. So octave 1 by 1 is like the basic resolution. It has poor resolution compared to octave 1 by 9. So each band, it has higher energy, but there are also fewer bands. But octave 1 by 9 has a lot of bands, and they have little energy. Each band has little energy. So the final result is you add more energy few times and less energy more times, and you get the same single value. It'll get clear with the calculation. So we do the same comparison for octave 1 by 1 and 1/3. We see some difference, but it's not drastic because octave 1/3 does not have a very high resolution compared to octave 1 by 1. It's just 3 times more. And then the same holds true for octave 1/3 and octave 1 by 9. So now let's view the mathematics. So here's a logarithmic addition. Let's say in octave 1 by 1, we were interested in 2000 hertz, which had a sound pressure level of 96.3 dBA. But in octave 1 by 3, we view the same 2000 hertz in 3 parts. That is 1600, 2000, and 2500. So we have different levels. And again, when we move to octave 1 by 9, we get even higher frequency resolution. So let's say if we want to construct octave 1 by 1 from octave 1 by 3 and octave 1 by 3 from octave 1 by 9, we can do so by logarithmic addition. So for example, let's start with octave 1 by 9. Let's say we know that this particular frequency 1600 is split into three octave parts. That's why it is 3 times higher resolution, and the same holds true here as well. But let's start with this frequencies. We have these 3 frequencies, and we have the sound pressure level. We add them up logarithmically, and we get the single value for 1600. That's how we arrive at this 88.2. And we repeat the same process. We add these 3 values, sound pressure levels, logarithmically, and we arrive at this. And again, we add this and logarithmically arrive at this. Now for octave 1 by 1, it is lower resolution compared to octave 1/3. And octave 1 by 3 is constructed by splitting this into 3 parts. So we add all these 3 values and we arrive at this value. So now you observe that when we are adding logarithmically, we're adding many energies together, and the final value goes up. So this 2000 is not just representing 2000, but rather it's representing a lot of frequencies in addition to 2000. So We cannot reach the conclusion that it's the 2000 that is responsible, but when you go higher and higher resolution, we see something else is responsible. So this is the logarithmic addition, and we can see the single values. The single values are always the same because octave 1 by 1 bands has only 11 bands. One third has 33 and this has 99 approximately, and each of those bands of 99 bands has lower energy compared to the octave 1 by 1 bands. So that makes sense. When you add many frequency bands of lower energy, you end up getting a single value, which is exactly same as adding fewer frequency bands of higher and higher energy values. So the end result is the same. So to conclude, octave bands with higher frequency resolution such as 1/3 and 1 by 9 provide more detailed spectral information compared to the lower resolution octave 1 by 1 bands. High frequency resolution means more data points, more processing time. But the single values are always the same. Now the question is, which one would you have to use for analysis? Well, octave 1 by 1 is the quickest because it has got very low resolution. It will give you a quick result. But then if you want to go deeper, you have to go to higher resolution analysis. You can't go to extremely high resolution because it also has a computational cost. So the trade-off, in my opinion, is octave 1 by 3 because you get it quick. You get a quick result. At the same time, you get a good frequency resolution, which is accurate. All right. Thank you for watching this video. I hope you enjoyed it. Have a great day.